All right, so let's record. Cool. So, those pictures that you saw in the beginning are related to something called the golden ratio. If you've ever done any exploration of art or music or nature, you've encountered the golden ratio, whether you knew it or not. And this came up in CSE215 last week. And yes, as someone just said in chat, this is related to Fibonacci numbers, which is where we're going to begin today. I want to look at Fibonacci numbers and how to generate these in a computer, and I want to look at how this can be a really slow process and how we can speed it up using something called dynamic programming. That's going to be the key to making our PA5 tractable. The knapsack problem is going to involve dynamic programming. So I want to go through that discussion, and then I want to run through a knapsack problem in gory detail and show you exactly how the algorithm works so that you can then go and write up code to implement this and turn that in for your PA5. So let's start with the Fibonacci sequence. And you may recall this is a sequence of numbers where basically each term in the sequence is the sum of the two previous terms. So you start with a pair of ones. 1 and 1 is 2, 1 and 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and it kind of goes from there. And it's an ever-growing sequence, and yeah, rated M for matrix, good. And it's got all kinds of wonderful symmetries inside. The square of a number is the product of the numbers before and after, plus or minus 1, and it alternates. And the ratio of these is a really interesting quantity. And it gets very close to this golden ratio that pops up in, artwork of Da Vinci and the spiral of galaxies and all kinds of other things. The ratio of female to male bees in a population approaches the golden ratio, 1.6 something. So it's a really interesting sequence, and it was developed, I believe, by studying rabbit populations and idealizing the growth rate of a population, and this is the count of the population over time. So for us, we would like to code this, right? Because that's what we do. We write code. And so this is not too hard to write code for directly. You basically need a pair of numbers, and at each point you just set your new number to be the sum of the previous two, and then you shift everything one spot. But since we're in CSE222, and we've been talking about recursion, we could write this up even more easily. So we can think of this as a recurrence relation, where we have the nth term of our sequence is equal to the sum of the two previous terms. So fn is fn minus 1 plus fn minus 2. But we need a base case, right? Just like with mathematical induction, you need a base case from which you can induct. We need to, at some point, specify actual values of this, because if I try to find f5, yeah, it's f4 plus f3. What's f3? It's f2 plus f1. What's f1? Well, it's f0 plus f minus 1. And what is f minus 1? It's f minus 2 plus f minus 3. We're going to descend down this rabbit hole forever. So we need to specify some particular values. So we can say f0 and f1 are both equal to 1, and then from f2 on up, we can define it as the sum of the two previous terms. So this is a nice recursive definition of our function, and it maps really nicely into recursive code. So my function for finding Fibonacci I is as follows. If I is less than or equal to 1, return 1. That's this base case right here. Otherwise, let's just return Fibonacci I minus 1 plus Fibonacci I minus 2. It's a trivial function, right? And we're not seemingly doing any work in here, but this actually will successfully compute the ith Fibonacci number. And this is, classic recursion where you kind of feel like you're cheating, because you're just saying, you know, well, I'll just use this Fibonacci function that doesn't exist yet. But if we believe this will give us the I minus first and I minus second number, then we are convinced that this will give us the ith Fibonacci. And so we can test this with just a little main loop. We'll just go from 0 to 45, and we'll print out the ith Fibonacci number. We'll save it in answer and print it out. And not surprisingly, this actually works. But the surprising part is how slow it is. And you can see the first few numbers, 1, 1, 2, 3, 5, 8, 13, 21. But it gets really, really slow. And it will finish Fib 45 in less than a minute. But, you know, you and I could add these two numbers together by hand to get the next Fibonacci number, right? And so why is this so slow? It's such a simple function, right? It's just saying take the two previous Fibonacci numbers and add them together. And yeah, surprisingly, it's not my PC. That's the problem here. So let's make a modified version of this, and I'm gonna modify this with one evil global called count, and every time I go into my Fibonacci function, I'm going to increment count. And when I come back and I report the value of the ith Fibonacci, I'm also going to record the value of count in my output and see how many times I called the Fibonacci function, because this is recursive, right? And so if I run this, you can see what's happening. The number of times I'm calling Fibonacci to find the 40th Fibonacci number is this huge number, right? So and this number is looking like a Fibonacci sequence itself, right? 9 and 5 is 14. Well, I had to do 15 calls for the next one. 15 and 25 is 40, and I had to do 41 calls for the next one. So the amount of work that's being done to calculate the nth Fibonacci number is on par with the nth Fibonacci number itself. And so this one I'm letting run beyond 45, and it's just going to get slower and slower and slower. And why is this happening? So besides, you know, the cost of you know, saving your local variables on the stack and so on, there's a more profound cost to recursion, which is just the number of times that you might recurse. So let's suppose I want to calculate the 6th Fibonacci number. To do that, I have to calculate the 5th and 4th. And to calculate the 5th Fibonacci number, I have to calculate the 4th and 3rd. And to do the 4th, I have to do the 3rd and the 2nd. And to do the 3rd, I have to do the 2nd and the 1st. And to do the 2nd, I have to do the 1st and the 0th. And these two don't require any recursive call. That's our base case. That's where we're just going to say, oh, let's just return a 1. So my recursion will end here and here. And this one will also not recurse, but this one will recurse. And this one will say I need to do F2 and F1, and F2 will require F1 and F0. And so to calculate F5, I'm making all of these recursive calls to my Fibonacci function. And then when I calculate F4, I'm going to use this subtree of calls to do that calculation, and then finally I'll take those two answers and add them together. And you can see the Fibonacci behavior of the workload, right? The amount of work I have to do to find this is the amount of work I had to do to find this, plus the amount of work I had to do to find that. In some weird sense, we could just look at CPU time and calculate Fibonacci numbers by how long this function takes to return without ever looking at the return value itself. All right, so that's the downside, but there's a way we can deal with this, which is, notice what's happening. To find F5, I calculate F4 and F3, but to calculate F4, I'm also calculating F3. Now, if I could save the value of this calculation, then when I was calculating F5, right, I find the value of F4 finally, I would ask to add the value of F3. I could say, oh, I already calculated that. I know what F3 is. It's such and such. You can prune your tree. you can get rid of that whole collection of calls. And similarly, once you've calculated F2, you can get rid of any other calls to F2. And once I've calculated F4, I'm not going to do all of this recursion down here. I'm just going to take that saved value. And so, yeah, you want to cache your numbers exactly. And fortunately, this is still working on Fibonacci 50. Fortunately, that's pretty easy to do. So here's a version of Fibonacci's that utilize this this caching property. This is something called dynamic programming with a typo. So what do? I have an array called save, and I'm only going to use this for up to the 1000th Fibonacci number. So my save array is going to save the first 1000 values of my Fibonacci function. And as usual with arrays in C, we need to initialize them, so I'm initializing them to 0. And I have a variable count which tells me how long the array is, because arrays don't have a length. And so I'm doing the same thing, right? I've got my global counter. I'm going to calculate the ith Fibonacci number, save that in answer, print that out along with the number of calls that were made. And my Fibonacci function looks the same as what it did before, right? But I've added a few extra lines. So what have I added? I added one line in the beginning here, which says check my save array, check my cache. And if the ith entry is not 0, don't do any recursion, just return that ith entry. And this is the same, and this is the same, and this is the same. But there's one extra step at the end here, which is after I've calculated my answer, which took a lot of work, right? That's where I go down and I do all of this recursion, and I make all these calls, and I come back and I say, okay, now I know what F5 is equal to. At that point, I save it. Right, I copy it into my array called save at index I. Now I had to do a lot of work potentially to calculate that Fibonacci value for whatever I was, but if somewhere in the future I ask for the ith Fibonacci number, right here I'm going to see that that value is saved, and I'm just going to return it, and I short circuit all of this hard work. Yeah, I made long, so these integers would be a little bigger, but they're still not big enough to do a lot of Fibonacci numbers. But they'll go bigger than 2 billion at least. It's global because I declared it outside of the main function, outside of any function. So this is global, and this is global. All right, so if we run this, right, it calculates the first 1000 Fibonacci numbers in almost no time. Now the numbers aren't accurate, they're rolling over because they're too big to fit in however many bits we have available. But it doesn't take any time. You can see the number of calls it's taking to calculate Fib 790 is 3. Why? Because it already calculated Fib 789 and 788. Yeah, the negatives are the rollovers. And this rolls over pretty quickly. So we're good up to here, and then Fib 92 is bigger than we can fit in a long integer, and so it becomes negative. It's a 2's complement thing. But the amount of work that we're doing, right, the number of times we have to make this recursive call has been pared down significantly. And you're going to need to do this in PA5 because the knapsack problem, the solution to it is kind of the same as this, but it's worse. You branch off, you know, however many number of items you have in your inventory, that many branches on each step. And so even a modest sized knapsack problem will not finish in any kind of lifespan. Unless you use dynamic programming, which is this caching of results. All right, does that make sense? All right, so let's go through a detailed knapsack problem example. And I want to do this to show you clearly what the algorithm is doing. Your goal for PA5 is to code this algorithm in C, right? But you can't code an algorithm unless you understand the algorithm completely. So I want to make sure we're absolutely clear on what this is supposed to be doing. Because a lot of times, you know, people are working on really large programs and they come to office hours and we're working through their code and we'll get to a point and I'm like, so why are you doing this? And the answer is something like, well, I wasn't sure what we were supposed to do there, so I was trying this, right? If you don't know the algorithm that you're after, you're probably not going to get it coded correctly. So at this point, Tuesday, right, 6 days before the assignment, I think your biggest goal should be understand the knapsack problem algorithm, which is this maximum value function. If you can understand exactly how this should work, I'm confident you can code it pretty quickly. There's no fancy data structures involved here. There's no linked list. There's no trees. There's no need to ever do a malloc statement. Okay? It's really, it's more of a 224 style program, except that it's recursive. And recursion, you know, is actually easier in some ways than iterative code. So we're going to use our inventory that we were playing with yesterday. So we have 3 items. I'm just going to call them item 1, item 2, and item 3. And we're going to have a weight and a value. And so item 1 is, I don't know, it's a pen or something, and it costs $2 and it weighs 1 ounce. Item 2 weighs 3 ounces and costs $9, and that's like a fancy pen. And item 3 weighs 4 ounces and costs $13, and that's a notebook, fancy notebook. So quick review, knapsack problem. The goal is you have a bag with a certain holding capacity. It can hold a certain amount of weight, and you have an inventory of items with different weights and values, and you want to know, how do I find the collection of items to put in my bag that maximizes the value, right? So you just won the shopping spree at the store, and they give you a bag that'll hold 20 ounces of stuff, and you can put in as many of any of these items as you want as long as the weight doesn't exceed 20. And you want to maximize your value. So should I put in, you know, a bunch of item 3? Should I put in 20 of item 1? What's the combination that gets you the best return? And it's not a greedy algorithm that works here, right? Item 3 is the most valuable per weight, right? This is worth 3 1/4 per ounce. Item 2 is only worth 3. Item 1 is only worth 2. So this is the most valuable item. But you can't maximize your profit by starting with as many of item 3 as possible. That sometimes leads to a suboptimal solution. And the example we saw yesterday was if your capacity is 6, if you start with the most valuable item, you get item 3, that's 4 ounces and $13. That leaves you 2 ounces, and you can't fit item 2, but you could fit 2 of item 1. So put in item 1, which is 1 ounce and $2. Put in another item 1, 1 ounce, $2. That's $17. But in fact, if you had simply put in 2 item 2s, you would get $18. So you can't be greedy, right? A greedy algorithm solves something by taking the best possible solution at each point, which would say, well, let's get the most value we can per ounce up front, right? You have to sacrifice that most valuable item and start with an item that's a little less than the most valuable, right? Only $3 per ounce instead of 3 1/4. But you can put 2 of those in and you get a bigger final answer. So our approach to solving this was to develop this, this maximum value function. which takes some integer capacity as an argument, and it returns what the maximum value is you can get from that bag. And we said that the way you can find this is to use a recursive algorithm. So if we think of this as, an array of weights and an array of values, we do the following. We argue that, well, we have to start off by putting one item in our bag. And we might put in item 0. And if we put in item 0, two things happen. We get the value of item 0 plus whatever we can extract value-wise from the remaining capacity of the bag. So this is our original bag's capacity. Item 0 weighs this much. So once we put item 0 in our bag, we've got this much value, and we've only got this much capacity left in our bag. And what's the most value we can get from that? Well, that's just max val of that capacity. So if we start with item 0, this is the most we can get. But if we start with item 1, then we get the value of item 1, and our capacity diminishes by the weight of item 1, and max val of that capacity tells us how much value we can get from the remaining space in the bag. And since we have 3 items, we could start with a third item, get the value of that, and then extract the maximum value from the capacity diminished by the weight of that third item. And so we calculate these 3 expressions, we find the largest of those, that will tell us the maximum value from our capacity. Okay, that's the high-level view of the max val function, which is what you need for knapsack. So I want to go through this in a particular example using this inventory table. And I also want to keep track of the inventory that gives us the maximum value. Because remember, the other 15 points, the final 15 points on PA5 is, in addition to knowing what the maximum value is, knowing how you get that. Knowing not just that it's $18, but that you get that by doing 2 of item 2. Right? And you can run the sample code, you can see this working on the server. So we want to keep track of the collection of items that gives us this maximum value. So we're going to use something like this. All right, so this is the memory of the computer, and we're going to keep track of what we're doing. So we're going to call our maximum value with some capacity, and we're going to calculate the maximum value, and when we're done, we're going to record the maximum value here and record the inventory of which, how many of each item we need to get that value out of that capacity. And this is going to want to go in some kind of structure that you're going to define, because each of these is going to be a function call to my max value function. I'm going to call with capacity, and it needs to return the maximum value and this inventory. So make a structure with, an integer for the value and an array of integers for the inventory. It's up to you, right? You get to design your own data structures. But it doesn't have to be anything fancy. There's no linked lists or anything like that. Simple arrays will work. And this is how I'm going to calculate. Now, I only have 3 things in my inventory. So we'll keep the inventory up there. And I only have 3 things to choose from, so I'm going to do my 3 calculations here. And these are going to involve recursive calls to max val. And when I come back from max val, I'll write down its number and the inventory that call to max val gave me. All right, and we'll turn this into something. So let's calculate. Let's suppose we're calculating max val at 10. I'm not going to go all the way through max val 10 because that's a lot of work. But we'll do 6 along the way, and we'll call it good then. But let's say we're calling our max val function with a capacity of 10. All right, and you really want to be tuned in and paying attention at this point, because this is going to go for 5 or 10 minutes. And if you tune in halfway through, it's just going to be really confusing what's going on. All right, so we're calculating max val of 10. So I'm calling this function with an argument of 10. We want to fill in max val and inventory. And our loop says, okay, we need to do 3 calculations. For item 1, if we put that in our bag first, we're going to get the value of item 1, which is 2. And then the weight of item 1 is 1. Our initial bag capacity is 10. If we put item 1 in our bag, our capacity is now only 9. 10 minus 1. So whatever the maximum value is we get from a bag that holds 9 ounces, if we add 2 to that, that's the value we get by starting off with item 1. But a second possibility is we start with item 2, which has a value of 9, and a weight of 3, which means that once we put this in our bag only holds 7 ounces. And so whatever max val of 7 is, we add 9 to that. That's the value we get by starting with item 2. Or if we put item 3, our notebook, into our bag, we've got $13 worth of stuff in our bag. And it's taking 4 ounces of capacity to hold that, so whatever we can get from the remaining 6 ounces, that'll be added to the value of the book, 13. And one of these will be our best solution. Might not be unique, but one of these will give us our best possible outcome. All right, well, we have to make recursive calls. Before we do any of this stuff, we would have called max val with an argument of 9. But I'm going to write these in while we're here so that we don't get confused. So let's call max val of 9. So where does this go? It goes on the stack, right? Literally, it gets pushed onto the stack, all of the information, the local variables, and we make a new call to the same function which says, hey, good morning, let's calculate max val of 9. All right, and the exact same thing happens. If we start with item 1, that's worth $2, takes away an ounce, and so we have to calculate max val 8. The next item is worth $9, takes away 3 ounces, so we have to calculate max val 6, and if we put a book in, that gets us $13, and we have to calculate max val of 9 minus 4 is 5. And this call to max val will push this on the stack and say, hey, let's find max val of 8. All right, so I'm going to pick up speed, but let me know if I do something wrong. So this is going to be 2, 9, 13, and this is going to be 7, and 5, and 4. And so our next recursive call will be max val 7. And our values will be 2, 9, and 13, and this will be 6, 4, 3. And these don't get terribly interesting for a few minutes, or for a few iterations. So this will be 2, 9, 13, and 6, take away a weight of, take away a weight of 1 is 5, take away a weight of 3, and take away a weight of 4 is 2. And so we need to find max val of 5. And so this will be max val 4, max val 2, max val 1. This is 13. Right? This is why we have computers, because we're not good at doing this. And this would be a really horrible job. Although people used to do this kind of thing for a living, guess what they were called? They were called computers. It was a job title. And it was a human who did, calculations. All right, so if our bag can hold 4, we can start with item 1, get $2 out of that, and have 3 ounces left. If we put in item 2, we get $9 out of that and have 1 ounce left. We can put in item 13, the book. We get $13, and there's no capacity left in the bag. But this is a possible solution. Okay, because we're allowed to use the last 4 ounces of capacity in the bag. But we can't let this go negative. All right, so we'll come to that shortly. Let's calculate max val of 3. And our stack is getting full now, right? But we have good stack capacity. So max val of 3, okay, we can put in item 1. That gets us $2 and leaves us 2 ounces of holding. We could put in item 2, which is worth $9, and uses all 3 ounces, so we have nothing left. But item 3 weighs 4 ounces, and our capacity is only 3. So we're not allowed to consider this third case where we put item 3 in our bag, and that's really important. If you go ahead and you put this in and you try to catch it later, you won't get the right result because it's not a valid solution. There's no way I can get my $13 value of item 3 from a bag that only holds 3 ounces because I can't put item 3 in that bag. So this is not a possible consideration. So in our for loop, or whatever kind of loop you're doing, right, there's a little caveat here, which we said yesterday, only do this if this is not negative. If the weight of your item is not bigger than the capacity of the bag. So you've got to take care of that in your coding, but that's just an if statement, right? And you know, you're finding the maximum of these. Here we're just doing it by, we're going to write down these numbers and pick the largest by looking at them. But in your code, you know, you need to record the first one and then compare the second to the largest, compare the third to the largest, and so on. So the usual drill. All right, so I need to find max val of 2. Now we're almost to the end of this. So max val of 2, well, I could put in a item 1, which gets me $2 and leaves 1 ounce of capacity. Item 2 weighs 3 ounces. My bag only holds 2. I'm not allowed to do that. And item 3 weighs 4 ounces. My bag only holds 2. I'm not allowed to consider that. So in this case, you know, whatever I get from this calculation, that's going to be my max value for a capacity of 2. Okay, but let's calculate max val of 1. And there's only one thing I can do with a maximum value of 1. I can put in a single copy of item 1. So that'll get me $2 and it will leave me no capacity in my bag. And again, I can't put in item 2, I can't put in item 3. Okay, now I'm going to make a recursive call to max val of 0. But in my code, I'm going to have a base case, which is going to say if capacity is 0, return 0. That's going to end my recursive descent down the rabbit hole. So this call to max val of 0, that's going to be one more recursion. I'm not going to write it out. That's going to come back right away and say 0. Okay, so I'm going to return for the first time from all of these recursive calls to my max val function. I'm going to return for the first time, and I'm going to know that max val of 0 is 0. And the inventory that goes along with that is simply no items 1, no items 2, no items 3. All right, so this information needs to come back from my max val function. And for the base case, just return a 0 and say you don't get to put in any of your items. All right, now I can do my calculation. All of that was to calculate MV0, which I just found out is 0. If I put item 1 in, 2 plus 0 is 2. That's the total value I can get starting with item 1. I need to look at the largest of all the cases I calculated. Well, I only calculated one case. And for that case, I found my maximum value is 2. So this is the value of max val 1. It's the largest of normally these 3, but in this case, just this one. All right. Here's the tricky part. In addition to recording the maximum value, we want to record the inventory that gets us that maximum value. How do we do that? Look at the inventory which got you this maximum value and bump up the count for item 1. All right, let me say it again and think about it. This inventory tells us how we get this maximum value. If we're choosing this solution corresponds to taking the maximum value you can get from this capacity and starting off with 1 of item 1. So whatever inventory gives us this max val, we want to bump up the count of item 1. So our solution for this is going to be the same as our original inventory, but we're going to increment the value of item 1's count. So this is going to be 100. That's the whole trick to keeping track of the inventory. Okay, it happens way down deep in the recursion, but it's really just getting back this item count from the max val function and then incrementing one of these based on which item gave you the maximum value. All right, this will clarify as we go forward. So we're done calculating max val 1. We know the value is 2 and the inventory is this. Why were we doing this? Oh yeah, over here we wanted to find max val 1. Okay, well we just did. We found max val 1 is equal to 2, and the inventory that gives us that maximum value is this, 100. All right, once again, our final maximum value will be 2 plus, max val 1 is 2, so 2 plus 2 is 4. That's the maximum value from bag of capacity 2. And what's the count of items that gets us that value? Well, take the count of items that gave us max val of 1, that's 100, and increment the count of item 1. So 200. And that makes sense, right? What is this saying? If your bag holds 2 ounces, the most you can get out is $4 by putting in 2 of item 1 and none of the other items. And we can see that from looking at the table. For one thing, capacity 2, the only thing we can put in is item 1. We can put in 2 of those and that'll get us $4. So this is looking promising as far as doing something meaningful. All right, so we return from our call to max val 2 and we come back to here. All right, so max val of 2 we've just discovered was equal to 4, and the inventory that gets us that value of 4 is counts of 200. Okay, so we've just finished this first calculation in our call to max val 3. Now we need to calculate max val 0. And again, that's a base case. We're going to come back with max val of 0 is equal to 0, and the item count there is all zeros. So now we can calculate these two sums. 2 plus 4 is 6, 9 plus 0 is 9. So which one gets us the greatest total value? If we put in item 1, we can get 6. If we put in item 2, we can get 9. This is our best solution. So this is the value that max val 3 would return. It'll say, hey, your maximum value is 3. And the inventory is that inventory that got us max val of 0 plus one more of item 2. Why item 2? Because that's the one that gave us the maximum value of all the cases we considered. So we bump up the count for item 2, and that's a 1. Okay, there's the solution for max val 3. Put in 1 of item 2, none of item 0, or none of items 1 or 3, and the maximum value you get out is 9. Okay, here comes our dynamic programming. So we've just calculated max val of 3. Max val of 3 is equal to 9, and the inventory that gets us that 9 is 0, 1, 0. Now our code is going to say, hey, I need to find out what max val of 1 is. Oh, and it'll do the addition. So max val of 3 is 9, 2 and 9 is 11. Okay, now it's going to say, hey, if I start with item 2, I can get 9 plus max val 1. It's going to call max val 1, and that's going to do a bunch of recursion. Okay, if we're doing dynamic programming, we've cached these values. So I would have been writing these down on another piece of paper, but I'll run out of real estate. But I can just kind of peek back through my call history, and I can say, oh yeah, I already figured out what max val of 1 is. Right? And I'm not going to do the recursion again. I'm just going to look at this information that I saved associated with a capacity of 1. I'm going to say max val 1 is equal to 2. And the inventory that gets me that is 1, 0, 0. All right, cool. Yeah, glad this is helping. All right, max val 1 is 2, 9 plus 2 is 11. And finally, 13 plus max val 0. Well, 0 is going to be our base case. It's going to come back and say there's no value you can get from that. The inventory is 0. 0 plus 13 is 13. So now our algorithm, as it's calculating this, looks for the largest, and when it gets to this one, it finds this is the largest of our possible values. So that's the value of max val 4 is 13, and the inventory is this inventory bumped up by 1 for the count of item 3. So item 3 goes to a 1. Depending on how you write your algorithm, what you do if they're equal is up to you, right? So if all three of these were 11, chances are if you write your algorithm to, consider things that are bigger than the largest you've seen so far, you would probably just end up taking the first one. If you say greater than or equal to, you would take the third. You'll get a different solution, but the maximum value will be the same in the end, right? So this will give you a maximum value. Yeah, you could randomize it too, and see where that gets you. So the item count might change, but the value itself will be the same, and that's reasonable, right? Right. So if I had, but in this case, if I had bumped this up by 1 in the count of item 1, it would say this comes from 1 of item 1, 1 of item 2. In this case, if this was the solution I returned, it would say take this, but bump up item 2's count. That would also be 1 of item 1, 1 of item 2. So those are actually giving the same solution. All right, let's do max val 5. This one gets to be more interesting. So it's either 2 plus max val 4, 9 plus max val 2, or 13 plus max val 1. Okay, well, we just calculated max val 4, and we found that max val of 4 was 13. And the item count that gets us 13 is 0, 0, 1. Max val 2 will go back to our cached value and say max val of 2 was equal to 4, and the item count was 2, 0, 0. And max val 1, we've saved this also somewhere, and we say max val of 2 is equal to 1, and the item count is 1, 0, 0. So we can do our calculations. 2 plus 13 is 15. 9 plus 4 is 13. 13 plus 2 is 15. So we have two solutions with 15. I'm just going to go ahead and take the first one and say, okay, our maximum value is 15. And the inventory that gets us that maximum value is the inventory that maximized 4 plus one more of item 1. So we'll increment this. There's max val 5. We're going to stop with max val 6. So max val 6 should be 2 plus max val 5 for our first calculation. So max val of 5 is 15. And the inventory for that was 1, 0, 1. Max val 3 we've also calculated, so we should have saved that somewhere. So we don't have to do all of the recursion. We can just say max val 3 is equal to 9, and the inventory is 0, 1, 0. And then max val 2, max val of 2 is equal to 4, and the inventory that gets us that is 2, 0, 0. All right, so let's calculate our three possibilities. 2 plus 15 is 17. 9 plus 9 is 18. 13 plus 4 is 17. And so this is our best maximum value, 18. So that's going to be the max val. And the way we get that value is to take the inventory that gave us max val of 3 and bump up the count of item 2. So we change this to a 2. So there's your solution for max val 6. And this is, this non-obvious fact that 2 of item 2 gets us our maximum value of 18. Well, there it is right there. 2 of item 2 gets you a value of 18. And we could keep unwinding the call stack, right? We could do these three values for, capacity 7, 8, 9, and eventually find out the solution for capacity 10. All right, so that's the whole algorithm. And you can get an idea, even with caching our values, there's a fair amount of work going on here. But if we're not caching, right, by the time we get here, we're going to have to do everything we just did just to find max val of 6. And to find max val of 7, we're going to have to do all that work again to find max val of 6, and then find 4 and 3, right? And then here to find max val of 9, we're going to have to find 8 and 6 and 5. And you can see if you're not caching your results, if you're not doing dynamic programming, you're getting a huge amount of work. So how do we cache these? This poor thing is still calculating Fibonacci numbers. Oh no, this is the fast one. So yeah, you can cache them with just an array. And I would recommend an array of some kind of structure. Make yourself a structure that can store a maximum value and an inventory of items. And what does that look like? Well, this itself can be just an array of integers. So I gave you a simplifying assumption, which is that there's at most 128 items. So you could just make a static array that holds 128 integers, initialize it to 0, right, and just use that array as your inventory. And so element 0 tells how many of this item, element 1 tells how many of that item, and so on and so forth. And then you can take that array of item counts, and you can take the integer of max val, and you can put those together into a structure, like someone just suggested in chat. Put those together into a structure and call that, you know, my answer, or something like that. And now make your max val something that returns an object of type my answer. And then your cache is simply an array. Instead of an array of ints, it's an array of my answers. And initialize it to 0, and so on and so forth. Yeah, and my answer would contain both the item, the maximum value, and the item counts, the inventory count. All right, so this is a good exercise in creation, right? This is here's what we want to do. Here's the types of information I need to keep track of and that I need to pass back from function calls, right? How should I do that? What kind of thing should my function return? Or should I pass a pointer to a structure and return the value by reference, right? You get to decide this. We can talk about particular possibilities, and we can go over code in office hours and so on. But it's up to you to figure this out, right? And that's part of the fun of programming, right? It's a creative process. It's a big box of Legos, and you're trying to make a castle. And, you know, where should the drawbridge go? I don't know. What shape should it be? I don't know. You get to figure that out, right? As long as when you're done, it's something like a castle, right? So here, as long as when you're done, you're implementing this algorithm. But there's a lot of wiggle room in there, and definitely take advantage of that and have fun with it. So this was a inventory file for the problem that we just did. So pencil, pen, and book. And if I do a knapsack of capacity 10 on that file, you see your best possible solution is to take one book and then 2 pens, right? So the book takes 4 ounces, the 2 pens take another 6, and you get a value of 13 plus 18 is 31 out of that. If you start off by trying to squeeze in 2 books, that'll get you a value of 26. It'll leave you 4 ounces, and all you can fit in there is 4 pencils, and or 2 pencils, and that'll get you a smaller value. That'll get you 30. Is there some algorithm you could find using the capacity mod weights instead of this algorithm? I don't think so. I mean, there are other ways to do this, but the kind of first order things that would work in some cases don't work in this, right? So trying to you know, mod out the number of books you can put in and mod out the number of pens, that's a greedy algorithm, right? And it'll get you a suboptimal solution. All right, so play around with that, right? Definitely work this out on paper, whiteboard, etc. You're more than welcome to do this part with friends, right? Hop on Discord if you want and come up with some sample problems and compare notes. Figuring out the algorithm, that can totally be collaborative, right? The only thing you got to make sure is your own work is when you actually start writing code, right? And that's got to be your own. But, you know, pseudocode, we've got some here. And working out specific examples, you can do that in groups with other people. And once you understand the algorithm, then go ahead, start writing some code. All right, we are out of time. Have a good afternoon. Come by office hours if you got questions. Otherwise, I will see you tomorrow. Thank you.